Hello there, Mr. Sutton here, bringing you the BC Calculus 8-1 Extra Practice Number 1 solutions on parametric functions. On this problem, I want the first and second derivatives in terms of t for this set of parametric equations. So to find dy over dx, I need y prime of t rather over x prime of t. So that's going to be, let's see here, negative 2 sine of t over 4 cosine of t. And just to make my life a little easier, I'm going to reduce this to negative 1/2. And also sine over cosine, that's really tangent of t. Now to take the second derivative, I need the derivative of dy over dx in terms of t. So derivative of this thing. But I also need to divide by dx over dt, x prime, in order to get rid of the dt and also square the dx. So derivative of negative 1/2 tan of t, that's going to be negative 1/2 secant squared of t. Downstairs, we're just dividing by x prime again, so 4 cosine of t. And I could leave it like this, or if I wanted to simplify this a little bit, so we've got essentially this cosine down here could come upstairs to be a secant, because secant's really 1 over cosine. So we have a secant cubed when all is said and done, and then negative 1/2 divided by 4, well, that's like multiplying by 1/4. So when the dust settles, then we have negative 1 over 8 secant cubed of t. On this problem, I want the first and second derivatives in terms of t for this parametric equation. So let me get dy over dx first. That's y prime of t over x prime of t. Y prime, using this equation here, that's going to be 3t squared. And then for x prime of t, that's going to be 2t minus 3, using our power rule. Not really an easy way to simplify this. So now I'm going to have to do the second derivative. That's going to require me to take the derivative of this thing. But then we also have to divide it by dx over dt, x prime of t in other words. So getting that numerator here, derivative of all this, I'm going to need the quotient rule. So let me set up my box and ribbon for that. I've got a numerator of 3t squared, denominator of 2t minus 3, and their derivatives, which are 6t, and this is going to be a 2 here. Using the ribbon to multiply all that out. And this is all happening in the numerator of this huge fraction now. So we've got 6t times 2t minus 3, and then minus 3t squared times 2, all of that over 2t minus 3 squared. Now all of this is being divided again by x prime, which is 2t minus 3. Cleaning this up a little bit, I've got, let's see, this is going to be 12t squared minus 18t. We already have a minus 6t squared over here, so 12t squared minus 6t squared is going to give us 6t squared. And then I also had a negative 18t up there, and I think that was it for what we had up there. Now this 2t minus 3 squared, that can come down here with the other 2t minus 3, and then that ends up being a 2t minus 3 cubed. And, I mean, you didn't have to simplify it, but if you did, there's your final answer. On this problem, I want the first and second derivatives of this parametric equation. So let me start with dy over dx. That's y prime of t over x prime of t. So y prime of t, that's going to be negative radical 3 sine of t. For x prime of t, we've got just negative sine of t. I can reduce that to negative radical 3, or actually positive radical 3, negative, so that's nice. Now to get the second derivative, I need the derivative of dy over dx divided by dx over dt, divided by x prime. That gets rid of the dt and squares the dx, which is what we need down here. All right, so derivative of the thing I just found, derivative of radical 3 is just 0. And now dx over dt, that again was negative sine of t. But as long as this doesn't have a value of 0 down here, we can have 0 over something that's not 0. So that's going to be 0, and that ends up being our final answer. For this problem, I want the first and second derivatives of this parametric equation set. So to make my life a little bit easier, I'm going to take this y of t and simplify it a little bit using some log rules. So since all of this stuff in here is being raised to the 4th power, I can pop that out in front of the log, and 4 ln of 3t is what I'm going with for this problem. All right, let me start by finding dy over dx. That's y prime of t over x prime of t. Y prime of t, the derivative of this new version I've written now, that's going to be 4 over 3t times a tail of 3, which is going to cancel out the 3 down there. For x prime, I've got 1 over 2t times 2. So this ends up being, let's see, 3's cancel, 2's cancel. So 4 over t over 1 over t. Doing a little same change flip, we've got 4 over t times t over 1. T's cancel, so that's just 4. And now I need to get the second derivative. That's going to be the derivative of this first thing in terms of t, divided by dx over dt, or x prime. Derivative of 4 is 0. And then dx over dt, that was, again, 1 over t. Doesn't really matter, though, because this stuff down here can't have a value of 0. So that means 0 over something that can't be 0 is going to end up being 0. On this problem, we want the lowest point on this parametric curve between negative and positive 2. So for lowest point, I'm talking about a y value. So let me find critical values for y prime then. Y prime, that's going to be 2t plus 1. And let me set that equal to 0. Subtracting 1, dividing by 2, we have negative 1/2. Now, if I plug in a number between negative 2 and negative 1/2, like negative 1, for example, this stuff's going to come out negative. So I'm negative between negative 2 and negative 1/2. If I plug in something between negative 1/2 and 2, like 0, well, now this stuff comes out positive. So y prime of t, we can say, is positive, greater than 0, between negative 1/2 and 2. So in terms of the motion of the particle, if my y prime is negative, that means our particle is going down until we get to negative 1/2. And then it's going up until the end of the interval. Well, if it's going down until negative 1/2, negative 1/2 is the time at which it has reached its lowest point. So that means that the lowest actual point is going to be whatever point I get when I plug negative 1/2 in for x and y. Let's go ahead and do that. Plugging negative 1/2 in for x, that's negative 1/2 plus 1, which is positive 1/2. Plugging in now for the y function, this is going to be, let's see, negative 1/2 squared is 1/4. And then we've got minus 1/2, that's minus 1/4 when the dust settles. So that's the lowest this point ever gets. For this problem, I have this parametric equation between 0 and pi, and I want the rightmost point. So that means I need to analyze this x of t function a little bit. Specifically, I'm going to take its derivative and find some critical values, and I'm going to try to maximize the x function. So x prime, that's going to be 2 cosine of t. I want to know where that equals 0, at least between 0 and pi. So this is the x values on the unit circle. That's going to be 0 at pi over 2, and also 3 pi over 2, but again, we're only looking between 0 and pi, so this is our only critical value on this interval. Now, doing a little mental sign analysis here, if I take the cosine of something between 0 and pi over 2, I'm basically in quadrant 1, so my cosine is positive. So we're positive from 0 to pi over 2. If I take the cosine of something between pi over 2 and pi, well, now I'm in the second quadrant, so that means we have a negative cosine, negative x values. So we're less than 0 between pi over 2 and pi. So in terms of the particle's motion, I'm going to the right with this positive x prime until I get to pi over 2. Then I'm going left for the rest of the interval. So the rightmost point then must happen at pi over 2. And that means that it's going to be whatever point you get when you plug pi over 2 into the x and the y function up here. X of pi over 2, well, that's 2 times sine of pi over 2. That's 2 times 1, which is 2. Y of pi over 2, that's cosine of pi over 2, which is just 0. So there we go. For this problem, we have a particle moving in the xy plane with a position given by these parametric equations here. And you'll notice the y has this weird k constant that we don't know yet. Now, we're told that the line tangent to the particle's path at time 3 has a slope of 8. Based off this, we want to know the value of k. So what I'm basically going to do is I'm going to set up an expression for dy over dx in terms of t, and then I'm going to set it equal to this slope of 8 when t equals 3. So for dy over dx, we're going to need y prime of t over x prime of t. Y prime, that's the derivative of kt squared. That's going to be 2kt. And now for x prime, that's the derivative of this ln of t plus 1. So that's 1 over t plus 1. And I'm also going to clean this up a little bit, multiply by the reciprocal. So I can rewrite this whole thing as 2kt parentheses t plus 1. All right, so I know that when I plug t in at time 3, so 2 times k times 3 times 3 plus 1, when this happens, we should have a slope of 8, they told us. So I'm just going to set this equal to 8 because that's the value it should have at time 3. Based off of this, I'm going to solve for k. So I have 2 times 3 is 6, times 4 is 24, so 24k equals 8. Dividing by 24 and reducing, we have k equals 1/3. So choice B. For this problem, we have some curve C defined by these parametric equations. We want the equation of the tangent line when time equals 1. So for a tangent line, I need an x and a y value and a slope. Let's start with the x and the y value. So we need x of 1, which is going to be 3 plus 1 squared, which is 4. We also need the y value at time 1. Plugging that into the y of t function, that's going to be 1 cubed plus 5 times 1. This is really 1 plus 5, which is 6. And finally, we need the slope, dy over dx. If we're starting with parametrics, then we can write that as y prime of t over x prime of t. Y prime, that's the derivative of y of t here. That's going to be 3t squared plus 5 using our power rule. And now for x prime, derivative of x of t, that's just going to be 2t. Can't really simplify or reduce that, so at this point all there is left to do is to plug in 1 for t and hope for the best. So if I do that, I have 3 times 1 squared plus 5 over 2 times 1. This is, let's see, 3 plus 5 is 8. We have a 2 down here. 8 over 2 is 4. So I have an x value, a y value, and a slope. I'm going to use point slope form to initially plug these in. Then I'll rearrange it to get one of my answer choices. So I have y minus the y value 6 equals my slope of 4 times x minus my x value of 4. And let's get everything over on the right side now and put it in slope intercept. So let's see, the 6 has got to move over to the right side. We just have a y by itself on the left. On the right side now, we distribute the 4, so that's a 4x minus 16, but now I'm adding a 6 as well. So minus 16 plus 6 is minus 10, which gives us answer choice B.